In previous presentations, we explored the foundation engineering of Mercedes-Benz Stadium in detail, from deep foundations such as drill shafts and auger cast piles to ground improvement methods like Bible piers. We've already examined how each of these techniques was applied and why they were selected in response to the site's challenging geotechnical conditions. Before we move on to the upper structure, the striking facet exoskeleton and the iconic retractable roof, we need to pause and understand something just as crucial: how all of these foundation elements come together to form a single unified structure system. This presentation serves as a crucial bridge. It connects everything we've explored about the grounds and prepares us to understand what lies above. The roof's ability to move and the bolt's ability to flex depend entirely on every force, every load and vibration being grounded safely through an integrated and carefully coordinated structural system. So today, we followed the story of structural connection and continuity from isolated foundations and piles through the towering mega columns and up to the first steel node of the retractable roof truss. What we are looking at is not just a collection of structural elements, but a system engineered to move together, resist together, and stand together. In some areas of the site, spread footings with a compressive strength of 4,000 psi could be placed directly on competent soil. But elsewhere, the ground lacked sufficient bearing capacity for even moderate structural loads. In those zones, engineers turned to spreads on geopiers, a solution that focused on improving the ground rather than resorting to deep foundation systems. To achieve this, they used a ground improvement technique that densifies weak soil by installing compact stone columns. Each geopier measured approximately 24 inches in diameter, with depths ranging from 10 to 20 feet, and offered allowable bearing capacity of up to 6,000 psi. These reinforced zones made it possible to support lighter structural elements such as cone core slabs and exterior walls, while still utilizing shallow foundations. In areas where the soil was soft and deep support was required, but space constraints or vibration concerns made driven piles impractical, engineers turned to auger cast in place piles. More than 1,900 auger cast piles, each with diameter of 18 inches, were installed throughout the site. These cast-in place piles were drilled to depths ranging from approximately 40 to 65 feet, depending on soil conditions. They provided load capacity of 150 to 220 tons, depending on location and geotechnical factors. Made with concrete strengths ranging from 4,000 to 6,000 psi, the auger cast piles offered the benefits of deep foundation support while minimizing the noise, vibration, and disruption typically associated with conventional pile driving. Their quiet, low-impact installation made them ideal for areas adjacent to sensitive structures or tight construction zones. But designing a strong foundation is only the beginning. It must connect seamlessly with the structure above, and that's where the real engineering ingenuity becomes evident in the connections between the foundation and the stadium's critical structural components. Let's begin with the precast seating units. These are stands visible throughout the stadium, precast concrete panels manufactured off-site and delivered for on-site installation. Each panel is placed atop a racker beam, a long sloping structure member that follows the angle of the sitting bolt. They are firmly anchored using steel plates and mechanical fasteners, ensuring stability even as tens of thousands of fan jumps, cheers, and move in unison. Moving further outward, the concrete bowl segments comprising the structure walls and platforms that surround the field were constructed using multiple concrete pours, even separate by carefully designed construction joints. These joints were reinforced with embedded steel and filled with grout to ensure structural continuity, allowing the entire bowl to behave as a unified system despite being built in discrete segments. Perhaps the most impressive connection in the entire stadium is the one between the mega columns and the deep foundations beneath them. Each column stands over 110 feet tall with a massive 15 by 30 foot cross-section and is designed to carry the enormous weight of the retractable roof, video hollow board, and lighting trusses. At the base, each mega column sits on a reinforced mat foundation between 7 to 12 feet thick, made of high-strength concrete rated at 7,000 to 8,500 psi. Beneath the mat, multiple drill shafts, each with 66 to 78 inches in diameter, extend deep into the ground. These shafts are capable of handling axle loads ranging from 2,800 to 8,300 kips. Assuming each mega column is supported by 16 drill piers with an average capacity of 6,000 kips, the total vertical load resistance per column can exceed 96,000 kips or roughly 427,000 kN. The integrated system, comprising the mega column, mat foundation, pile cap, and drill shafts, acts as a single unified unit, a cord into bedrock, ensuring maximum structural performance under vertical, lateral, and uplift forces. This integrated design allows each mega column to support between 3,000 and 4,000 tons of concentrated load from the retractable roof. Thanks to this structural continuity, the system functions as a unified structural element capable of resisting not only the massive vertical loads from above, but also the bending and shear force generated by winds, structural movement, and seismic activity. Each column features thick, reinforced concrete sections behaving more like vertical structure cores than conventional columns. So now let's walk through a single load scenario. Imagine a sudden gust of wind striking the roof during a game. That wind creates pressure on the roof panels, which is transferred into mega columns. The columns that convert that force, part vertical and part lateral, into reactions at their base. The foundation resists these reactions through the strength of the drill shafts and the combined effects of soil pressure and friction surrounding them. Meanwhile, at the same moment, the crowd in the stand is cheering and moving. This activity imposes distributed loads on the precast seating units. The load then travels through the racker beams into vertical structural elements such as columns and walls, and ultimately reach the foundation below. In the area where the soil was improved with geopiers, these loads and safely dissipated with minimal settlements. This is the stadium's load pass, an unbroken chain from the top of the roof to the rock below. What's brilliant about it isn't that it uses new materials of flashy technology. It's that every connection was designed with purpose, even transition reinforced for continuity, and every force accounted for. Mercedes-Benz Stadium is more than just an engineering project. It's a structural narrative. It tells the story of how diverse foundation methods were orchestrated to overcome complex geotechnical challenges. It demonstrates how structural components, whether cast in pile, prefabricated, or fabricated in steel, can be integrated to create cohesion from complexity. It proves that even a structure with a retractable roof, vast crowds, or extraordinary spans can remain stable, resilient, and enduring. This is what makes Mercedes-Benz Stadium more than just an architecture landmark. It is a case of study in integrated structural design. From drill shafts to mega columns, from geopiers to racker beams, it illustrates how discrete elements can align to form a continuous load pass from the ground all the way to the roof. In our next presentation, we'll shift our focus to the upper structure, exploring the facet, exoskeleton, and mega trusses. These components are not merely architecture gestures, they are fundamental to completing the stadium's structure framework. Today they reveal how exterior framing and long-span systems contribute to both structural performance and architecture impression. Thank you.